Recorded is rolling. Welcome to Tuesday Week, Monday, September 22nd. So we're going to take the next 3 days, Monday through Wednesday, to do a couple of labs that each have two parts. So two-part labs we'll pace out over 3 days. It's going to be pretty good. Right, so I want to run through these with you guys, show you guys how to set these up, how to think about these, what questions you're trying to figure out. You guys have a paper that's on one side, friction lab, the two parts, and on the other side is this Atwood lab, two parts. So I'm going to put that with you guys. Okay. All right, so AP students, you guys, I do want you guys to do an AP style write up for one of these four. All right, one of these four. Now, to really help you guys out, nearby within reach probably are actually the write ups for the two parts of the friction lab. Okay, so you can have the answer key in one of these, but I do want you guys to think critically on what would be the next step. How would you just do it? So you pull out like piece of paper and write up, and as you go along, you can check your stuff. I do have these for the friction write-ups. I guess if you want to challenge yourself a little bit more, you could do the Atwood write-ups, which I don't have write-up for, right? But do one of these four, right? And then you can just staple that to your lab page and then turn this in by the end of class Wednesday. Can you guys do that? Right. So if you guys more practice on that front. Right. You guys, this textbook puzzles. I'm looking at tentative due date of next Friday. I think we'll align with exactly how long it'll take us to finish this section. And I do want to do a bunch of these with you guys in class. And in fact, a lot of these look kind of like the labs that you're doing today, or that you guys were back on Friday. We covered 3 puzzles. Right, so that covers really most of those puzzles there. Between those. All right. So questions so far? What's going on? All right. So let's look at this. All right. Let's start with friction lab. So the question is, which you don't have spelled out here, but I think you can figure it out. Or actually, if you're looking at here, actually, I got the question right here, right on this page that's also within reach of you, right? And so, what's the coefficient of friction between two surfaces? Right? Now, it's the same question regardless of what the setup is, right? What's the coefficient of kinetic friction? So it looks like, guys, kinetic friction. Will the two surfaces be sliding past each other? Yeah, that's what kinetic friction is, right? Static friction is you haven't broken the friction yet, which is usually a higher value, right? Right. So there's 2 ways to set this up. Right. So once here, and I have little diagrams here. So one setup is that you very simply drag the weight horizontally across the surface, right? And this was what the free body diagram looked like. Oh, by the way, I did over the weekend rearrange these formulas. Right. So here's all the forces. Okay? So whatever weight you got boxes of lab weights. Okay? There would be some weight pulling straight down. So for example, this one should be 5 newtons. But you could take a spring scale, right? Spring scale, a bunch of spring scales back here. You could hold it up, right? And this is going to read about 5 newtons for this one. Okay? Therefore, if it's resting on a horizontal surface, what is the normal force also equal to? 5 newtons for this particular weight. If this is 5 newtons, this would have to also be 5 newtons, wouldn't it? Okay. Suppose you're dragging with so that there's constant velocity, and that's key. Because guys, constant velocity means the net force is equal to what? 0. Right? 0 net force, 0 acceleration can be constant velocity. So as long as you're pulling constant velocity, what that means is that this force here is equal to this force here. Right? The applied force that you can read straight off the spring scale would also indicate the friction force, right? Wouldn't it? Right, so you guys know how to get all these forces? You guys can? Right? And the coefficient of friction is the ratio of these two right here, which is the same thing as the ratio of these two right here. Wouldn't that be it? You guess it? Okay. Now, so I have a table where you can record this data, and I have a graph set up. It says what's the pulling force versus the weight. If you want to, you can call this friction force versus the normal force, because it would be the same graph effectively. Right. Actually, that might be a better version, better title. Okay. We got a couple of questions down here, and ultimately trying to figure out what's coefficient of friction. Okay, you guys see that? Okay. Now, the other half of this lab, the one on the right side of this page, can answer the same question, what's the coefficient of friction? But this one is conceptually, a little more involved. Okay? So you need to find some tiltable surface. This could be your desk. If you students just tilt your desk. See students go back to the library and maybe use a textbook and look at the textbook. Right? Now, keep in mind that the materials matter. So if you want to compare apples to apples, maybe have the same materials going on. Like if you're using your desktop versus a textbook cover, right? Those will be different, right? But you should have some protractors lying around. If not at your desk, in the back of the lab table, or if you need one, let me know. I've got like 30 of these floating around somewhere. Okay, so you can measure what is this angle, which is this angle, and this would be the free body diagram. Right? This is the last thing you guys saw back on Friday before you took off for the weekend. Okay, so it's the last thing in your notes. Okay? So there's guys, how many proper forces are on this weight right here? 3. Okay, weight down, the normal force off on an angle, and a friction force holding in check. Okay, in fact, if it's sliding at constant velocity, what do all the forces sum to? 0, 0. Okay, which means this: is this normal force equivalent to the mg cosine theta?
Yes.
Yeah, and is this friction force equal to what? Mg sine theta. Okay. But you know what else you know about friction force compared to normal force is that they're related by this coefficient of friction. Is it? Okay. So I'm covering up part of this poster. I want to see if you guys can get this from scratch, but it's hanging in my room anyway. So if you need to, you could look over on that wall where this answer is. Okay? And there's this series of steps. This would actually be a really good free response question. I would not be surprised at all if AP asked this in May. If they say, find the coefficient of friction using this exact method, and you have to do a write-up where you explain. You can do this whole thing with one tool, just a protractor. That's really all you need. All you need is a protractor for this. Okay? That might be a question. How can you figure out coefficient of friction with nothing but a protractor? Okay? So there's this step-by-step derivation. Once you guys can figure this out, and then how do you get to this last step? Of course, you're looking at it right here, but here, I'll do it with you guys just to make sure that everybody's for sure got this. Okay? So if we look along, say, if I call this like the x-axis, okay? When this friction force minus this mg sine theta have to zero out, okay? And then, okay, so I can slide this over. So friction force would be equal in magnitude to mg sine theta. But I also know friction force is coefficient of friction times normal force. Well, if I'm talking about kinetic friction, that's true. That's this one right here. Substitute right there. Okay? And then normal force is equal to this mg cosine theta. There's another substitution. So it's a bunch of little substitutions. And then right here, guys, what cancels out on both sides? Interesting. So I'm making the claim. You can test this because you guys will do the empirical science the next few days. Okay? Does the live weight actually cancel out itself? I'm claiming here that it doesn't matter how much weight you're talking about. Right? Maybe the materials matter, but that's okay. Is that all right? So that's the friction half of the slab. Now how about the Atwood? Right, so there's 2 parts to the Atwood. So the classic Atwood, I have a really cartoony version of the. Now you really want the string to be probably about a meter long. Okay, can you guys take a pulley, take a string about 1 meter long, hang a couple of lab weights on both sides? Can you guys do that? Okay. So the question you're trying to figure out here, okay, and you can see it's all the way to the bottom. You're trying to address this. Find the relationship among the acceleration, the gravity field, and M1 and M2 using the starred columns. You guys see there's like 4 starred columns here, and then on the modified version, there's also 4 starred columns. Okay? There's some way you can multiply and divide these starred columns to result in the acceleration. Okay, so let's go across this table, right, step by step. What are you looking at? Okay, so I'm giving you Earth gravity in centimeters per second squared. Ooh, wouldn't that be 980 centimeters per second squared? Okay. All right, what are the 2 lab masses used? No, okay, I want this to not be blurry. Okay, go on. Okay. All right, so I'm listing grams here because that's probably a reasonable number to work with. As long as everything's in grams, you're looking for a proportional answer. Okay, so what's the difference? And I put absolute values because it doesn't matter if it's going clockwise or counterclockwise. Right, what's the sum? Right, that'll only be important. Okay. Right, so you guys good so far? Okay. Now here, little side thought. Guys, what if these were the same mass? What if you put like 100 grams, 100 grams? What's it going to do? Yeah, so 0 net force, 0 acceleration. It's just going to sit there. It's not going to move at all. All right, that might. Okay, so that's sort of like one data point, right? What if you did this? What if you put 100 grams on one side and you just left an empty string on the other side? How much would this accelerate straight down? Yeah, it should be the full rate of gravity, which is like right here, right? Okay, so those are sort of boundary conditions. Those would be extreme conditions, somewhere between 0 and pure free fall. Could you ever get this to accelerate more than pure free fall? I don't think so. Okay. Okay. So how about the right 4 columns on this table? Now these are like kinematic, right? So they're going to lead to calculating the acceleration going through kinematic motion. So how far does it fall? Like if you make the string a meter long, could one of these weights fall up to a meter, and the other one would go up a meter, wouldn't it? Right. So one falls down a meter, the other falls up a meter. Right? So that could be like 100 centimeters, maybe. That could be a reasonable value, right? Ooh, I'll give you guys some stopwatches. Could you do like 3 times and take an average? Can you guys do that? Right? Okay. And then guys, if it starts from rest, starts from rest. You know how far it goes and how much time. Could you calculate the acceleration? Right? And I'm really helping you guys out because I showed you guys how to do it above this column, how to calculate that. Start with h equals 1/2 at squared. Right? Now, this a is not the pure free fall anymore. It's whatever it's actually accelerating. Okay, there's that. Right? You can calculate the acceleration. And then how do you tie all these together? How do you tie this acceleration that you calculated from kinematic motion to, okay, it does have something to do with the gravity field that we're in. Okay. And something to do with the sum of difference of the weights. There's some way you can multiply and divide those where they're all matching to be the A. Okay? Let's do that. Okay. All right. Then I've got this modified setup. Now, if you look back at the ladder, or actually I got one here, I got this low friction cart. I guess these wheels, it's like low friction cart here. Now, I'll tell you that this has a mass of 500 grams just empty by itself. There's also a triple V balance back there. One of these sitting on it. I think right now it's rating like 498 grams. That's not 500 grams, right? Just empty. Now, you could, of course, stack more weights on it. Wouldn't that give it more inertia? More inertia, harder to get it going. Ooh, more inertia, right? Okay. You could also, throw one of these over the side of the table. I've got most of the setup there for you, and maybe hang like a tiny lab weight right here. Okay, picture. And then now this is a little bit different setup, so the table's a little bit different, but the big picture is the same, right? You got some masses hanging on. You could say how far does maybe one of these fall and how much time, 3 times take an average and calculate the acceleration. Right? So all the kinematic bits the same. You guys get that? Okay, you're trying to chase down what's the acceleration as a function of these two masses, right? Which is going to be a little bit different from, right? Like these two scenarios are a little bit different. They'll have a little bit different equations being one thing. Like I said. Let's make practical matter. What would be easier to have a huge weight on top and a small weight hanging down, or a small weight on top and a huge weight hanging down? What would be easier to time with the stopwatch? Yeah. Put the huge, maybe I should say mass up here because the weight cancels out from the normal force, but the huge inertia, huge mass up here, and a little tiny weight that very slowly pulls it down, so it gives you a long time interval. I bet that would be more accurate with the stopwatch, wouldn't it? I guess. Okay. And let's see, do I have the? Yeah, I got some posters around here related to these Atwoods. So the classic Atwood, right here, I'll give you guys the pink box. Here's a hint. When I eventually drive this for you guys like a debrief, it has something to do with Newton's second law of motion. There's some way I can get it from there. Right, there's some related formulas. Here's what the free body diagram looks like. So different weights. Right? There's a tension holding everything together, but I didn't create a space for that in your lab because it turns out you don't need that calculated tension to figure this out. Right? We'll solve some textbook puzzles that look kind of like this in CYT, right? But the answer to your lab is right here. I'm covering this up because I want you to see if you guys can figure this out. And similar setup on the modified Atwood. Right. So this one looks a little different. Right. You can still derive it through dynamics with Newton's second law of motion. You get what's the acceleration of the system, sort of. Right. All right. So see if you guys can figure those out. And okay, I think I told you all the setup you need to know. Is there any questions so far? Okay, you guys good? All right. So I'm gonna close down this recording, walk around, help you guys out. So pace yourselves out because we're doing these two-part labs over 3 days. And I'll walk around, help you guys out.
We should have the first one left today.